Okay, so here we have three different vehicles. We have a truck here in the white. We have an SUV or hatchback car here in the orange, and then we've got a race car here in the blue. So just looking at these, we know that, okay, that truck is probably going to experience the most drag, then the SUV, and then the race car. Now, drawing the forces here, this truck, if the wind is blowing at the truck here, and the truck is moving this way, we'll say V truck, and then V wind, then we're going to have a drag force. The drag force is going to be against the direction of motion of the truck. And it's probably going to have a lot of drag force just based on this shape. So the truck is huge. We can approximate this as a rectangle. So we'll say that this here is the width of the truck, and this here is the height of the truck. And this is like almost exactly a box shape. So rectangle's a pretty good approximation. We do see that the mirrors stick out on the side, the wheels kind of stick out at the bottom, but for the most part, we're going to approximate this as a rectangle because it's not worth getting into the little details of those things. Now, for the car actually looks a little bit more like a trapezoid. So, if we draw, it kind of goes, we have sort of like a box shape, and then we've got this sort of trapezoidal shape on top. So if you wanted to get real detailed with this, you would approximate this as two shapes, and you would need to know each of those sizes. So even though, and we can see this from the front of the car, that basically the hood and the front bumper here where the lights are and all that sticks out way farther than the windshield, and then the windshield is slanted. Those things will affect the CD and not affect the A. So as far as the A goes, that area, then we're just looking at the two-dimensional view from the front or the back. So it's something like this. If you have the car going with speed of V car, and then you have the wind blowing here with speed V wind, your drag force is going to be, again, against the direction of motion. But you can see here that this car is much likely to have a much lower drag coefficient than the truck, just because of its shape is a lot sleeker. And now this race car, for sure, this race car is like really has not very much bumper here at the end. So the wind is going to be able to travel very nicely along there, and it's not going to be getting stuck as much here, but it's going to, similarly to the airplane, it's going to be able to travel like that. Okay, so we'll do some examples now. So we'll be given some parameters and then calculate drag force. For all the vehicles, we'll say that they're traveling at the same speed through the same air, and then we will give them different areas and different drag coefficients and see how their drag forces compare. So let's say that all of these are traveling in air. So density of air, 1.225 kilograms per meter cubed. And maybe they're all traveling at speed V equals 60 miles per hour. So 60 miles per hour is about 25 meters per second. We'll work in metric units here. We'll approximate all of these as a rectangle. So for that frontal area. So now we need to be given some different parameters. So here for the truck, we'll say that the drag coefficient for the truck equals 0.8. We'll say that the width of the truck is 2.2 meters, and then the height, h, equals 2 meters. Now for this small SUV here, we remember from before that drag coefficient for a car is between 0.2 and 0.3. Since this is an SUV, we're going to say it is about 0.3. So it would be slightly on the higher end of that. Width of this equals 2 meters. And then height, we'll say here is the width. And then here is the height. And just for simplicity, we're going to call this a rectangle. And the height here equals 1 meter. And then the race car, this should have the lowest drag coefficient because it's got that sleekest shape. So we'll say that one's on the low end of the cars and 0.2. And then the width here will be the same as the SUV, we'll say 2 meters. But the height, we can tell obviously that the height is lower, and we'll go with 0.8. So if we're given all of those, and we will say that there's no wind, so just totally speed of the car, no wind. So even though there's no wind, it'll still have a drag force because the car is moving. We need to find the drag force on all vehicles. So the general formula here is drag force equals negative 1/2 rho CD V squared A. So we will work out the car one here because we have the most space. And we'll say that the drag force equals negative 1/2 times the density, which is 1.225. And then the CD from this white formula here, which is the drag coefficient. So that's going to be 0.2. And then the V, which we said was 25 squared. And then the area, which is just W times H. So we'll have times 2 and times 0.8. And this gets us that the drag force for the car equals negative 122.5 newtons. And so if we do the same thing for this SUV, we will get that the drag force equals 230 newtons. And that is negative if we're talking directions. And then for the truck, here we have 1/2, 1.225 times 25 squared. And then the A for the truck would be we need the CD, 0.8. And then the area is 2.2 times 2. And so that gives us that the drag force for the truck equals negative 1347.5 newtons. So just looking at this, we calculated that the truck has the largest magnitude of drag force. The SUV has the middle, and the race car has the lowest. And as a reality check, that should make sense because just we know that race cars have low drag, and we know that a truck or a bus is going to have high drag. So that gives us some confidence that our answers are correct. Now, one thing that we can notice here is the drag force is proportional to velocity squared. Pretty much everything here is a constant except for the velocity. So while the truck is moving, the density of the air does not change. The drag coefficient does not change. The area of the vehicle does not change, but the speed of the vehicle can. So the drag force is not able to be approximated as a constant because as the vehicle speeds up, the drag force goes up by a squared term. As the vehicle slows down, the drag force also goes down. So it's not even a linear relationship. So we can do if we look at a simulation of this, then, so if we put in certain things, so we can say our speed is 25 meters per second, looking at the drag coefficient going from 0.2 to 1.0, density of air is 1.225. This will just kind of give us an approximation. So here we can see a three-dimensional view of drag force. So this shows us speed on the y-axis here. We have drag coefficient on the x-axis, and then we have drag force on the z-axis. So you can see that as the speed increases, then we have an increase in drag force. That is not a straight line. I'll rotate this around. That is a curved line. It is parabolic. And then as the drag coefficient goes up, then in that case, we do have a straight line. That is a linear relationship, the force versus the drag coefficient. But the higher your speed, the higher your drag coefficient, the greater the force is. We see that peak right here. And looking at the two-dimensional plots, we can see here the drag force for different drag coefficients, where the highest drag coefficient is here, we get the highest force. The lowest drag coefficient here, we get the lowest force, and the speed increasing. We can see that how the drag force relates to the speed is a parabolic relationship, which we should expect because of the v squared that goes into that calculation.